Right. So in the last module, we were discussing the time evolution of a quantum mechanical system, and we discussed that the time evolution of the quantum mechanical system is determined by solving the time-dependent Schrodinger equation, and the most general solution of the time-dependent Schrodinger equation can be written as psi of x comma t as a general linear combination of the separable solutions or the stationary states psi n, phi n in this particular form, right? Okay. So what is the general strategy that one employs? Remember that if I call this some psi n of x comma t, then this is nothing but n cn psi n of x comma t, but the psi n's are called stationary states, owing to the fact that probabilities and expectation values and stationary states are just constants or time independent quantities. So how does one go about constructing this general solution? Well, one has to choose the constants Cn very carefully, right? So how does one choose the constants Cn? So again, this is also something that we discussed when we talked about the Laplace equation in the electrodynamics portion of this course. You solve for the Cn's by looking at the boundary conditions. Okay. So in this case, what are the boundary conditions? Suppose, so usually in solving such problems, you'd be given what the system is at stay at time t equal to 0. So suppose if you're given what the solution of the system is at time t equal to 0, you're supposed to find what the wave function is at any other time t by looking at the general solution of the time dependent Schrodinger equation. So you fit psi of x0 to this general solution at time t equal to 0. What is this general solution at time t equal to 0? At time t equal to 0, this t becomes 0. So the general solution is nothing but Cn psi n. So this is nothing but Cn psi n, right? So using this boundary condition, you can evaluate what these Cn's are. So this tells you determine, this is the equation that determines the Cn's, okay? Now, on the face of it, this might seem like a very crazy claim because there is many different Cn's, right? For each particular stationary state, there is one constant Cn. So with just one condition, psi of x comma 0 equal to this infinite sum, how can I determine all these Cn's? Well, the magic of this lies in the fact that these psi n's are the Eigen functions of the Hamiltonian operator. And the Hamiltonian is a Hermitian operator. So these psi n's are orthogonal. In fact, they're orthonormal wave functions. So one can use this orthonormality of psi n's to determine all the Cn's, even though this is just one equation. So I will demonstrate this in the context of a very simple example. So the general strategy when it comes to solving the time-dependent Schrodinger equation is to simply write it as a linear combination of all the stationary states and figure out what the Cn's are by fitting it to the boundary condition at time t equal to 0. So the only thing that remains is to determine what these psi n's are, and these psi n's are the Eigen functions of the Hamiltonian operator. And this, of course, depends on what potential energy that we are talking about. So the determination of psi n depends on the problem at hand. So in this module, we will solve for the psi n's for the simplest case. And the simplest case is one for which the Hamiltonian operator is the simplest. Remember, the Hamiltonian operator is p square over 2m plus v of x. So we'll solve it for a very simple case. And this simple case is actually extremely instructive and surprisingly very useful in many real-world situations in quantum mechanics also. And this goes by the name of particle in a box. So this is the problem. So I'll tell you what the problem is. Now, assume that the particle can go only from some specific point to some other specific point. Imagine that there is an infinite potential barrier at this point and at this point. Okay. So this is V of x, and this is x is equal to 0, and let us call this some x is equal to, let us say, L. Now what this means is that let us assume that there is a single quantum mechanical particle stuck in this potential. What is this potential? Well, at x is equal to 0, there is an infinite potential barrier. So the particle cannot go to negative values of x. At x is equal to L, there is another infinite potential barrier. There is some infinite force acting on the particle at x is equal to L, which doesn't allow it to escape x is equal to L. So the particle is trapped between x is equal to 0 and x is equal to L. Okay, it can only move between x is equal to 0 and x is equal to L. So this potential barrier height V is infinity at x is equal to 0 and x is equal to L. But inside the region x is equal to 0 and x is equal to L, the particle is basically free. Okay, the potential is 0. If the potential is 0, obviously it means there is no force acting on the particle, so the particle is basically free. Okay, so the potential energy function of this particular particle in a box scenario is such that V of x equals 0 if x is less than or equal to, where x is between 0 and L, and infinity otherwise. So the particle is basically free to move inside the box, but outside the box, the particle can never be found. So since the particle can never be found outside the box, in the regions beyond x is equal to 0 and x is equal to L, in this region and in this region, obviously the wave function has to be 0. Because remember that the probability of finding the particle is psi square, right? And psi square can be 0 only if psi is 0. So beyond x is equal to 0 and x is equal to L, the wave function should be identically equal to 0. So we are required to solve for the Schrodinger equation inside the potential box. So outside the well or outside the box, psi equal to 0. Inside the box, we have to solve the time independent Schrodinger equation. What is the time independent Schrodinger equation? Inside the box, it is h psi equals e psi. H is p square over 2m, which is minus h bar square over 2m d square psi over dx square plus v of x times psi. V of x is a potential, but inside the box there is no potential, there is no force, so v is 0. This equals e psi. Okay, since v of x equal to 0 inside the box. Okay, so this is a very simple scenario that one might expect. So I can rearrange this equation, and you should by now know how to solve this equation, or at least know what the solution is. This is minus 2me over h bar square times psi. Okay, and I will call this 2me over h bar square some k square. So this is equal to minus k square psi. Okay, because I'll assume that the energy of the particle is greater than 0. So the solution of this equation is, again, this is a very simple harmonic equation. D square psi over dx square equals minus k square psi. So you know that the solution of this is psi of x is a sine kx plus b cosine kx. Or equivalently, I can write this as a e to the ikx plus b e to the minus ikx. So the question is, what is A and what is B? How to determine A and B? Once I know what A and B are, I know what the solution to the time independent Schrodinger equation is. And I'm done. Well, ordinarily, if you have such barriers, the way you would construct the general solution is by appealing to the boundary conditions. So assume, for instance, that these barriers were not infinity, but were of some height v0. Okay, then of course the particle can be found outside x is equal to 0 and x is equal to L. So on the left and the right, let us call this regions 1, 2, and 3. Of course, if the barrier height is infinity in regions 1 and 3, the wave function is 0. But if the barrier height is not infinity, but some 5 or something like that, some finite number, in regions 1 and 3, of course, the wave function would not be equal to 0. So in such cases, you'd have to solve the time-independent Schrodinger equation in region 1, region 2, and region 3 separately, and you have to match these solutions at the boundaries. What does this mean? This means that at the interface x is equal to 0, the solution that you obtain by solving the Schrodinger equation in region 1 should be the same as a solution you obtained by solving the Schrodinger equation in region 2. Okay, so this is the statement that the wave function must be continuous. Not just the wave function, but the first derivative should also be continuous. So usually you determine this constant by demanding that psi of x and d psi dx are continuous across the boundaries. Okay, this is what you usually do. Why d psi dx? Remember that the Schrodinger equation is a second order differential equation, right? So if a function has to have a derivative, it has to be continuous and differentiable. If the function has to be differentiable up to second order, f of x should be differentiable and continuous, and df dx should also be continuous. Only then the second derivative is valid. So both psi and d psi dx should be continuous across the boundaries. Okay. Of course, this is a very trivial example in which the potential head is infinity, so the wave function is 0 in regions 1 and 3. So simply demanding that psi equal to 0 is sufficient for us. So we have two boundary conditions. Psi at x is equal to 0, which I will call psi of 0 equal to 0, and psi at x is equal to L, which I will call psi of L equal to 0. Okay, at the point 0 and at the point L, the wave function has to be 0. Now you might be wondering why at the point 0. Well, remember that the wave function has to be continuous across the boundary. So if it is 0 at psi equal to L plus 0.001, then we had to match these solutions. And in region 3, it is psi equal to 0, and so for the solution in region 2 to match the solution in region 3, this solution should have the same numerical value as a solution in region 3, which is 0. So at the boundary, this should be 0. Similarly, the boundary x is equal to 0 should match with the solution in region 1, which in this case is also 0. So these are the two boundary conditions we have for the particle in a box problem. Okay. So let us now fit the general solution that we have obtained with the two specific boundary conditions that we have deduced. So psi at x is equal to 0 is nothing but, at x is equal to 0, sine k times 0 is 0. So this is nothing but b. Okay. Now, if this has to be equal to 0, the only way this is, because cosine 0 is 1, so psi of 0 is just b. The only way this can be 0 is if I set b equal to 0, right? So this equation tells me that b equal to 0. So my solution is not a general combination of sines and cosines. The cosine part does not respect the boundary conditions. I have to throw it away. So the general solution is nothing, is only psi of x is a sine kx. Okay, but that is not all. I also have to impose the second boundary condition. What is the second boundary condition? Psi at L equal to 0, which tells me that a sine KL equal to 0. Now I can satisfy this by, this is my 0. I can satisfy this by claiming that A is 0. But if A is also 0 and B is also 0, the general solution is just 0. That's a trivial solution. So we don't want that. So we don't want A to be 0, but I want to be able to satisfy this equation by demanding that sine KL is equal to 0. And if sine KL equal to 0, this tells me that my constant KL is an integer multiple of pi. Okay, because sine n pi is identically equal to 0. So the second boundary condition tells me that the value of k that I have chosen is not arbitrary, but it has to be n pi divided by L. Okay, but what is k? If you go back, k square is nothing but 2me over h bar square. That is our value of k. So this k square then has to be n square pi square over L square. But k square for us is nothing but 2me over h bar square, and this has to be equal to n square pi square over L square. This tells me that the energy of the particle E is not some continuous number, but it is actually discrete. So I'll call this E sub n, and this is equal to n square pi square h bar square divided by 2ml square. Okay, so this is the energy of the various stationary states of the particle in a box. These are the energies that the particle can take, not anything else. So the energies are said to be energies, energies are quantized in multiples of pi square h bar square over 2ml square. Okay. So the lowest possible state has energy E1. Notice that n cannot be equal to 0. Okay. Why cannot n be equal to 0? Because if n equal to 0, I get a trivial solution again. Now, the lowest possible state has n equal to 1. This is called the ground state, and the ground state has energy E1 equal to pi square h bar square over 2ml square. The first excited state has n equal to 2, and this has E2 equal to 4 times pi square h bar square over 2ml square. The second excited state has n equal to 3, and this has 9 times pi square h bar square over 2ml square, and so on and so forth. Okay, so these are the energies of these different states. So we have deduced what the energies of the stationary states are. But what are their wave functions? The wave functions are sine of x equals a sine n pi x over L. Okay, because the energies are quantized, k is just n pi over L. So a sine kx in this equation simply becomes a sine n pi x over L. So how do you determine A? You determine A by the normalization condition. So you demand that the particle has to be found somewhere between 0 and L. So integral psi square dx has to be equal to 1 between 0 and L. Sin of x mod square dx has to be equal to 1. And if you use this, you will actually get that your value of A is nothing but square root of 2 over L. So you can write down your normalized Eigen functions for this problem as sin of x equals square root of 2 over L sine n pi x over L. These are the Eigen functions, and the Eigen energies are n square pi square h bar square over 2ml square. Okay, so this is the solution for the particle in a box problem. These are the wave functions corresponding to the different stationary states, and the energies of the stationary states are given by n square times the base multiple pi square h bar square over 2ml square. Okay. So now some comments are in order about the solution. So the first comment is that if you graph these wave functions, you'll actually see something very interesting. You'll actually see that the first ground state wave function is basically has no node. So it will be something like this between 0 and L. Okay. And the first excited state has exactly one node between 0 and L. This is actually a very general statement. At exactly in the middle, it will have one node, the first excited state. The second excited state will have 2 nodes and 3 nodes and so on and so forth. In general, an nth wave function would have n nodes. Okay. All right. So yeah. So the reason this happens is actually quite, it's easy to state that an nth wave function should have n nodes, but it's a little tricky to prove. So we will not prove it in this course, but you can actually demonstrate this very clearly using this example. The another thing to note is that the wave functions, as you go up in energy, are alternately odd and even and odd. So the ground state wave function is even. Okay. The first excited state is odd. Odd means if I flip it around L by 2, I get the opposite signs. And the next one will be even, and next one will be odd, and so on and so forth. And there is a very beautiful symmetry argument for this, because the Hamiltonian that we started with is symmetric under parity. So the Eigen functions should also be parity eigenstates. So this is a slightly advanced concept. So if anyone is interested, we can discuss this during the live discussion sessions. Okay. Now, another very important comment is that these are what are called bound states. Okay, so in general, quantum mechanics admits 2 different kinds of states: bound states and bound states and scattering states. Okay, so scattering states are those for which the particle just goes away at keeps freely traveling. For example, at x is equal to plus minus infinity, the particle can still be found. Okay, so these are very tricky states because by definition, if the particle can be found at x is equal to plus minus infinity, the wave function is not normalizable. So we have to look at these states very carefully. Bound states are slightly easier because bound simply means that they have to be bound within a region. So in this case, the particle is bound between 0 and L, so the wave functions cannot be found beyond L. So in general, bound state wave functions are 0 at x is equal to plus minus infinity. Okay, in this case, it is trivially true because the particle cannot go beyond 0 and L, but in general, you can have bound state solutions for the Schrodinger equation, which correspond to the fact that the particle cannot travel indefinitely. It is bound by some potential in some specific region. So the bound state wave functions have the characteristic. So the bound state wave function have the characteristic that the definition of these guys is that psi as x goes to plus minus infinity would be 0. Okay, so this is an example of a bound state wave function. Now the other important comment is that these states psi n are mutually orthogonal. So what does this mean? So psi n's are mutually orthogonal. So this means that integral psi n star psi n dx equals delta nm. So we'll try to understand what this means. This is a very important property, and this property is what tells you how I can determine an infinite number of Cn's even though I have only one boundary condition. So what is this property? So let us take the wave function corresponding to 2 different states, one corresponding to energy E1 and one corresponding to energy E3. Okay, or in general, some EM and EN. So construct psi m star psi n integral dx, and this will be nothing but 2 over L, integral 0 to L. There is a factor of square root of 2 over L from every energy eigenstate. So there is an overall factor of 2 over L, and this would be sine m pi x over L times sine n pi x over L dx. Okay, we'll now assume that m is not equal to n. M is not equal to n. Okay, now using some basic trigonometry, I can convert this into an addition of two cosines. So this will be cosine m minus n pi x over L, minus or plus, minus, I think, cosine m plus n pi x over L dx. Okay, so using some simple trigonometry, you can establish this. What will this be? This will be equal to 1 over L. Integration of cosine simply gives you sine. So this will be 1 over m minus n pi over L, which will be L over m minus n pi sine m minus n pi x over L between L and 0 minus again L over m plus n pi sine m plus n over L pi x between L and 0. Okay. Now remember that m and n are integers. So m minus n is also an integer. M plus n is also an integer. So sine of an integer, so at the upper limit, sine m minus n x over L at L and 0 is sine m minus n, sorry, pi, right? Because x is L, so L and L will cancel, minus sine 0. But sine integer times pi is 0, sine 0 is 0. So at both limits, this is equal to 0. So if m is not equal to n, psi m star psi n dx is identically equal to 0. Okay. Now, if n equals m, you have to do the calculations slightly differently. You cannot simply put m equal to n at this stage. You have to first start by assuming that m equal to n. So let us look at psi n star psi n dx. But you already know what psi n star psi n dx is, because you have used the fact that psi n star psi n dx is 1 to determine the overall coefficient a. This is just the probability that the total probability that the particle can be found anywhere inside this box. So integral psi n star psi n dx, which is square root of 2 over L 0 to L sine square n pi x over L dx is manifestly equal to 1. Okay? Because we fixed the coefficient 2 over L by assuming this property. So if m equal to n, psi m star psi n star psi n is 1. If m is not equal to n, psi m star psi n is equal to 0. You can combine these two equations into one equation by claiming that psi m star psi n dx is equal to delta nm. It's called the Kronecker delta function. Delta nm is equal to 0 if n is not equal to n, 1 if n equal to n. Okay, so this is called the Kronecker delta function. Okay, so this is the discrete analog of the Dirac delta function. Dirac delta function tells you that delta of x is an infinite peak at x is equal to 0 and 0 everywhere else. Delta nm tells you that it is equal to 0 everywhere for all n not equal to m, and 1 if n equal to m. Okay. So the fact that these functions psi n of x, these functions for various values of n, are a set of orthonormal functions, orthogonal normalized to unity. If both these are satisfied, it is called orthonormal set of functions. Orthogonal means integral psi m star psi n is 0 if m is not equal to n. Normalized to unity means integral psi n star psi n is equal to 1. Okay. So what does this orthonormal set of function give us? Remember that we discussed a few lectures ago that Psi n of x is basically the Eigen functions of a Hermitian operator, the Hamiltonian operator. So I can expand any other function f of x as a linear combination of the Eigen functions of a Hermitian operator. So suppose if I have some function f of x, I can always write this f of x as some a n psi n of x in this exact basis. Okay, so I can write this as square root of 2 over L integral Cn sine n pi x over L. Okay, in the space between x is equal to 0 and x is equal to L, sine n pi x over L as a set of orthonormal basis functions. Excuse me. So how does this solve my original problem? Remember that someone gives me the wave function of the state at time t equal to 0. So I am given psi at time t equal to 0. This is given to me. Okay, this is given. So using this, I'll have to figure out the general solution to the time dependent Schrodinger equation, which is Cn psi n of xt. Okay, remember, for the particle in a box, what is psi n of xt? This is equal to n equal to 1 to infinity, because there is an infinite number of states. There is no upper bound on n as such that the problem gives us. Cn, what is psi n? This is square root of 2 over L sine n pi x over L e to the minus I e n t over h bar, where En is n square pi square h bar square over 2m L square. Okay, so this is the general solution of the time dependent Schrodinger equation for the particle in a box scenario. So my job is to figure out what these Cn's are. If I know what the Cn's are, I know what the general solution is, and I'm done. So I need to be given some input to determine the Cn's. The input that I'm usually given is the wave function at time t equal to 0. So suppose if at time t equal to 0, this is some function, this is given to me. Using this, how can I extract the constants Cn? Well, that can happen very easily. So I will fit the general solution psi x comma 0. I will write this again as a linear combination, but if I'll put the time t equal to 0 in this equation, if I put time t equal to 0, the above equation becomes square root of 2 over L integral sum n equal to 1 to infinity Cn sine n pi x over L. Okay, or I can write this as n equal to 1 to infinity Cn psi n of x. Since I put time t equal to 0, e to the minus I e n t over h bar will simply give me 1. Okay, so I am fitting the general solution psi of xt that I have derived for this particular problem with the boundary condition that is given to me at time t equal to 0. So the way I have this equation. Okay, psi of x comma 0 equals this. So I have to determine Cn's. The way I'll determine Cn's is by using the orthonormality of the psi n's. So I'll multiply both sides by psi m star and integrate. Okay, what is psi m? So what is the left hand side? I'll integrate it in 0 to L psi of x comma 0 psi m star of x dx. This is the left hand side. Psi of x comma 0 is a function that is given to me. Psi m star is given. I know what psi m star is. It is sine m pi x over L, and I can trivially do this integration. Of course, I don't have to take the star because these are real functions, sine n pi x over L. But since we will also apply the same trick to general solutions that can also have complex wave functions, I'm putting the star in. This is equal to the right hand side is sum over n equal to 1 to infinity Cn integral 0 to L psi m star of x psi n of x dx. But remember that integral psi m star psi n between 0 and L is nothing but delta n n. It is equal to 1 if m equals n, and if it's equal to 0 for all other values of m. So this m is arbitrary, but we have a summation over n. But notice that the only term in this infinite sum that contributes is that for which n equal to m. Okay, whatever m star we have chosen, the n has to match that m star, otherwise the integration is 0. So this infinite sum collapses into one particular value for which n equal to m. So this is basically Cm. The left hand side is basically Cm. Okay, the only way this right hand side can be non-zero is if n equal to m, and for that particular value n equal to m, you have so basically if I want to make this more explicit, I will write this as sum n equal to 1 to infinity Cn delta nm, but delta nm is 0 for n not equal to m. So this only picks one particular value from this infinite sum, which is Cn. And that's it, I'm done. Because now I know how to calculate the Cm's. To calculate the Cm for a particular state, I will simply take the integral 0 to L of the star of that particular wave function m, psi m star, with the function that is given to me at time t equal to 0. So with this formula for the expansion coefficients, also called Fourier coefficients, I am finally done with the general solution to the problem of time dependent Schrodinger equation. This is nothing but n equal to 1 to m Cn psi n of x e to the minus I e n t over h bar, where psi n of x is nothing but square root of 2 over L sine n pi x over L, where en is nothing but n square pi square h bar square over 2ml square, and where the Cm's are given by this particular formula. Cn is integral psi n star psi of x comma 0 dx. Okay, so this is how you would go about solving the general solution of the Schrodinger equation given the solution at time t equal to 0. So you would simply take the time independent Schrodinger equation, calculate all the normalized eigenstates, and calculate the energy eigenvalues of each one of these states. Eigenstates because these are the eigenstates of the Hamiltonian operator. Okay, and then you simply construct a general linear combination of all such separable solutions like in this equation. And to determine the expansion coefficients, you simply plug in the given boundary condition at time t equal to 0 that was given to you, and calculate the expansion coefficients using this Fourier trick in the blue box. Okay, so this is the step-by-step solution of a given problem in quantum mechanics to determine the time evolution of a system. You first solve the time independent Schrodinger equation, you get all the energy eigenstates and the corresponding energy eigenvalues, and then you construct the most general linear combination with some expansion coefficients, and use the Fourier trick or the orthogonality of the wave functions to determine what the expansion coefficients are, and basically you can now construct the solution to the general problem. Okay, so usually this is why the time independent Schrodinger equation is of fundamental importance, because once you know the solution of the time independent Schrodinger equation and the boundary condition at time t, initial condition at time t equal to 0, I should not say boundary condition, I should say initial condition at time t equal to 0, you can construct the general solution of the Schrodinger equation. And the particle in a box situation here helps you illustrate this problem in a very simple setting. Okay, so for now we will stop. And in the next lecture, we will try and understand how to get the idea of a free particle in quantum mechanics. In some sense, a free particle should be the easiest of all, but you will actually find that there is some tricks lurking there. There is some hidden subtleties. We will try to uncover those hidden subtleties and understand how to construct the free particle solutions of the Schrodinger equation in the next module. We will stop for now.